Here they actually calculated the slopes, but C and D, A and B, E and F, correct answers. All right, so we've got a question again, position versus time graph. So now we're not dealing with velocity versus time, position time. Tell us the scales are both the same for all four graphs. For which cases, if any, is the position 0 at the indicated point? So again, the point is right here, right here, 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 and here. So how do you get position from a position graph? Yeah, you look at the y-axis. Sometimes it is that simple. How do you get velocity from a velocity graph? Just read the graph. Just read the y-axis. So, or do any of these graphs have a position 0 at the indicated point? C, absolutely. Don't convince yourself that it's a trick question. Sometimes it really is that simple. It's a given. Read it. For which cases, if any, is the instantaneous velocity equal to 0 at the indicated point? So now, here's the question, how do you get velocity from a displacement graph? Slope. So substitute the word velocity or slope for velocity. Where do I have 0 velocity? Where do I have 0 slope? E. Because right there, the slope tangent to that is 0. Obviously I have a positive here, positive slope here, positive slope here, negative slope here. Here it's 0, and here it's negative again. So I've got E there. Where is the instantaneous velocity negative? So what am I looking for now? Negative slope. Which of these have negative slope? F and D. Or D and F if we go alphabetical. For which cases, if any, is the speed increasing throughout the entire time? So D, I have a negative slope, and is that negative slope getting more negative or less negative? So if the slope is getting, it's approaching 0, what is it doing? Slowing down. So B, I have a positive slope, and it's getting more and more positive. So I have positive velocity, positive acceleration. Yes?
At the point earlier when we did the circle thing, it was like this with positive acceleration. There was positive acceleration with velocity increasing.
Positive acceleration and positive velocity. Yes, this would be positive velocity, positive acceleration.
D as well. Yeah, that's what it was. D as well.
D would have a negative velocity
Positive.
and positive acceleration.
So positive, that means velocity increasing.
No, positive means if the signs are different, that means it's slowing down. If I'm traveling in the positive direction, if you're traveling in your car, you have a positive velocity, you hit the brakes, your acceleration is negative, you're slowing down. But you could also be traveling backwards, you're in reverse in your car, you have a negative velocity, you hit the brakes, you're slowing down again, but now you have a positive acceleration. So if we go back to the, go back 2 slides. We're looking for where the speed is increasing throughout the entire time. So if they have the same sign, then the speed is increasing. So we're looking for a graph that looks either like this or like this. So the speed increasing, definitely B, because we have positive velocity, positive acceleration. And with F, we have negative velocity, negative acceleration.
What about A?
But A, what's the concavity of A? Is it concave up or concave down? Or neither? If there is no concavity, then it's not accelerating. So A has a constant slope. Which means it has a constant velocity. And constant velocity is another way of saying no acceleration or zero acceleration. 35 minutes. All right. So, as I alluded to earlier, getting acceleration from a displacement graph is one of the more complicated or one of the more confusing tasks. So there are the explanations C, E. The last one says the magnitude of the slope is increasing. It's either increasing, becoming more and more negative, or it's increasing, becoming more and more positive. So that would mean that it's speeding up. If the magnitude of the slope is approaching zero, then that means that it's slowing down. That means velocity and acceleration are opposite sides. Which of the following represents an object having zero acceleration? The axis is a little bit hard to read on this one. This is a displacement versus time. This is a velocity versus time, velocity versus time, and velocity versus time. So when you get something like this, always first identify what type of graph it is. Are they all the same, like we saw in the ranking task? Or now they all kind of look similar, but the y-axis is different for graph A. So describe what's going on with graph A. Displacement versus time graph.
Velocity increasing. Yeah, it's velocity.
Yeah, your displacement is increasing,
Yeah.
the slope, it's a constant slope, right? And slope from a displacement graph gives you what? Velocity. So constant slope, constant velocity, that's a way of saying what? No acceleration. So for A, we have no acceleration. So that's at least one of them. Now let's look at the others. The other three are all velocity graphs. How do you get acceleration from a velocity graph? What characteristic of a velocity graph gives you acceleration? Slope. So we're looking for zero acceleration. So we want zero slope. So B, C, and D. Do any of these have zero slope? B, yeah. Negative slope, negative acceleration. Positive slope, positive acceleration. So the answer here is going to be A and B. Questions on that one? All right, so we've got another velocity versus time graph. Over the 9-second interval, can we say that the speed of the particle only increases, only decreases, increases and then decreases, decreases and then increases, or remains constant? How do you get the,
Is it only increases?
The speed of particles decreases and increases.
yeah, look at the section right here. It starts with a velocity of what, about -2.5, so it's traveling backwards at -2.5 meters per second. And then its velocity at about 4 seconds is what? 0. So it's moving, and instantaneously its velocity is 0. Speeding up or slowing down? Yeah, if your velocity is approaching 0, you're slowing down. So looks like it's slowing down. What's its velocity here at 9 seconds? 4. So if you go from 0 meters per second to 4 meters per second, what do you do? Increasing. So you're speeding up. So down here, slowing down. Up here, you're speeding up. So you're decreasing because you're approaching 0, and then you're increasing because you're getting further away from 0. Describe the slope of this line. Positive, negative, 0? Positive. And slope from a velocity graph gives me acceleration. So this is a good example of, down here I have a negative velocity, positive acceleration, and I'm slowing down. Up here, I've got, my velocity is above the horizontal axis, so I've got positive velocity. I still have a positive slope, speeding up. A very common graph that you'll see is something that looks like this, a velocity graph. Negative slope means negative acceleration. From here to here, it's approaching 0, so it's slowing down. Take a ball, toss it up in the air. On its way up, it has a positive velocity, but it's slowing down. At the apex, its maximum height, what's its velocity? 0, and then it starts coming back down again. This red line that I just drew is exactly what that graph would look like. Negative slope, negative acceleration. The slope of that line, if it's an object in free fall, is going to be negative 10 meters per second squared, dg. But by the way, in all of your notes, they use 9.8 meters per second squared per g. I'm going to use 10 because that's what AP Physics requires. I have requested that the notes be revised, but they have not yet. So the velocity is negative, the acceleration is positive from at the beginning, so its speed is decreasing, and then once they're both positive, it becomes increasing. This is a velocity versus time graph for a 0.5 kilogram object traveling along a straight line. The graph has 3 segments, 1, 2, and 3. Rope exerts a constant force of magnitude Ft on the object along its direction of motion the whole time. During segment 2 only, a frictional force is also exerted on the object. A lot of distractors in this problem. Ultimately, what the problem is asking for is wanting to rank the displacement for the three segments of the object's motion. So what we're looking at is the segment 1, segment 2, and segment 3. During which segment, or which one had the greatest displacement, which had the least displacement, and which one it was in the middle. So how do you get displacement from a velocity graph? Look at the area. So in a graph like this, you don't really have to calculate the area. Usually on a problem like this, you can just visually inspect. You know, draw the three separate areas that you're looking at. Which one of these is greatest? 3. It's taller, has the same width, so 3 would be the greatest. Which is greater, 2 or 1? Yeah, 2, because you could take 1, if you rotated 1 about the axis, you know, you would end up with, you know, 1 is going to be a line from here to here. So 2 has this little bit of incremental area. So 3, and then 2, and then 1. If you wanted, you could go in and, like for 3, you could break this into a triangle and a rectangle. Figure out the area of that triangle, 1/2 base times height, add in that rectangle. For 2, you've got, again, a triangle and a rectangle. For 1, you just have a triangle. And so you add up all those individual areas, and that would give you the total displacement of this object. You could solve it using kinematic formulas, but you'd have to actually calculate the slope, and that would be a much more tedious way of doing it. So the answer is A. They actually did find the areas: 4 meters, section 2, 5 meters, section 3, 6 meters. But if you're just asking you to rank them, you can just visually look and inspect the areas, and usually that would be sufficient. All right, so we're looking at some acceleration graphs. Which of these graphs shows constant positive acceleration? How do you get acceleration from an acceleration graph? The y-axis. And so what do you want the y-axis to be doing? You want it to be constant, right? You don't want it to change. Do any of these graphs show a constant positive acceleration? 1, yeah. It's positive and it's not changing. So, number 1. Which of these graphs shows 0 acceleration? 5. Yeah. How do you get acceleration from an acceleration graph? You read the graph, the y-axis. So 5, there is no acceleration. Which of these graphs show a changing acceleration? 2, 3, and 4. You know, the acceleration changes from here to here, from 0 to something, from 0 to something. A would actually have a jerk, meters per second cubed, you know, rate of change of acceleration. So 2, 3, and 4. So motion graphs, learn a few rules, a few key techniques. They're not terrible, but they can be confusing. Biggest mistake is probably applying the rules for one graph to a graph of another type, or not looking at what type of graph it is initially that you're being asked questions about. Interpreting a velocity graph as a displacement graph, or vice versa. I actually mentioned rate of change. Sure. Kinematic equations. When I teach these, I leave off the little x subscripts. I'd say V is equal to V naught plus AT. I separate my vertical and horizontal slightly different way. And turns out that these work for motion in the x direction, also for motion in the y direction. For this one, I take x, that's my final position, minus x naught, my initial position. Final minus initial anything is delta, and typically on a problem like this, what you're going to know is what the displacement is, how far this object. So solving for delta x, I've never encountered any difficulties with that. So I say delta x is equal to v naught t plus 1/2 at squared. Again, leaving off the little x subscript. And for this one, v squared is equal to v naught squared plus 2a delta x. I don't think I've ever seen a problem, have you, where they give you the initial position and the final position and plug them in? Or if they do, solve that offline. Have you seen that, Lee?
I'm sorry, repeat the question?
This is the official formulas you'll see on the AP formula sheet.
Yeah.
And they list x and x naught, the final position and the initial position. I always just use delta x, and I've never
Yeah.
run into any issues.
Yeah, I do that too.
Because typically a problem, it can say, it starts at 2 meters and it ends up at 10 meters.
Yeah.
It'll say it travels the distance or displacement of 8 meters. So. Notice each of these has acceleration, acceleration, acceleration. And these are all true for constant acceleration, which is what you'll see. The only time you might get into non-constant acceleration would be if you're in like AP calculus or AP Physics C, calculus based. Nobody in here is in AP C. It's not offered many places at all. So our kinematic variables, we have V, V naught, A, T, and delta X. We got 5 of them. Oftentimes what's more useful to observe about these 3 kinematic formulas is what's not there. So I've got V, V naught, A, and T. I have no delta X. There's no displacement in this one. For my next one, I do have displacement, V naught, T, and A. Then on this one, I have no final velocity. So if you have a problem where they give you the initial velocity, but they don't give you the final velocity, and you're not asked to calculate it, this one might be the candidate. And this one, I've got both velocities. I've got A, I've got delta X, but I have no time. Or this is the timeless equation. So when you're working kinematic problems, list your variables, look at what you have, what you're being asked to calculate, and which one is not mentioned at all, and that will drive you towards one, typically towards one of these. So if there's no mention at all of T, you don't need it, they don't give it, you're not asked to calculate it, go for the timeless. They don't mention the final velocity, but they give you the initial velocity. Then the second one is a good candidate, or if there's no mention of displacement or how far this thing travels, then the first one is a good candidate. Notice that if you do have, or if you have no acceleration, the first is just going to end up V is equal to V naught if acceleration is 0. That's not very useful. The last one, if I have no acceleration, I get final velocity squared is equal to initial velocity squared. Again, that's not real useful because this second term drops out. But if I've got no acceleration here, I end up with delta x is equal to V naught t. That one is useful. That's something moving at a constant velocity. I abbreviate this, distance is equal to rate times time. It's called the third formula. When we get into the projectile motion, you imagine the equal sign is an E or an I third. So when I list my kinematic formulas, and I keep them on the board pretty much all year, we prefer kinematic 1, 2, 3, and our honorary kinematic third formula, which is just a special case of kinematic 2 where you're moving at constant velocity.
Paul,
Yes?
can you address where you would have, where you're missing the initial velocity, but you have a final velocity, which is basically another version of the middle equation? You know where the sign changes right there? Where you have plus 1/2 AT squared, but there's another one that has minus 1/2 AT squared. You know what I'm talking about?
Not exactly. That's not something
There-
that
It's in some books.
Okay.
It's a
Well, the-
secondary form of that. Where
Yeah,
you're,
if you look at some books, there'll be the 5 kinematic equations, the 6 kinematic
Right.
equations, and what they boil down to are slightly different iterations of these. But these are the ones that you'll see on your AP formula sheet. And so I've not encountered a problem that can't be addressed
Okay.
via one of these. But good question. So if I refer to kinematic number 1 or number 2 or number 3, they're basically these in that order.
So,
And a lot of detail, I'm not going to drain this slide. As you're reading a problem, you got to be able to identify, oh, well, that's the velocity. Well, is it initial or final? Or that's a displacement, or that sounds like an acceleration. Question number 8. This is on page 16 in your notes. Racquetball strikes a wall with a speed of 30 meters per second to the right and rebounds in the opposite direction with a speed of 26 meters per second. The ball is in contact with the wall for 20 milliseconds. What is the average acceleration of the ball during the collision with the wall? So, racquetball strikes the wall with a speed of 30 meters per second. What does that sound like? Velocity, and that sounds like a lot like an initial velocity. Rebounds in the opposite direction. It's a terrible looking arrow. Speed of 26 meters per second. Sounds kind of like velocity too, doesn't it? And that's going to be my final. If it's in the opposite direction, what do we need to make it? Negative. So the final velocity is negative 26 meters per second. The ball is in contact with the wall for 20 milliseconds. What's that? Time, sure. 20 milliseconds is 0.02 seconds. What is the average acceleration of the ball? We're looking for acceleration. And what's missing? What variable did I not miss? Delta x. Do we have a kinematic that doesn't have delta x? Sure. First one. So v is equal to v naught plus at. Final velocity, negative 26 meters per second. Is equal to the initial 30 meters per second plus a times 0.02 seconds. Plug all that in, you get acceleration of negative 2,800 meters per second squared. So I doubt you would see, in my experience on the AP exam, very few pure kinematic formulas or kinematic problems like this. You're more likely to encounter a graphing problem, maybe a ranking problem. But this is good old fashioned, you identify your variables, like, what did I do?
how'd you do that?
The dots. Well, I said negative 26 minus 30, negative 56.
Subtract the 30 from both sides and then divide it by 0.02.
Yeah, I got to this point, and then this is just algebra. Solve for A. Anybody need to see that? So they solve for A. Acceleration is delta V over delta T, final velocity negative 26 divided by negative 30 divided by. Yeah, sometimes it's easy to get confused with positive and negatives and subtract when you should add, or add when you should subtract. Or identify both velocities as positive, which will give you most likely one of the other answers. You have a question?
So you don't manipulate your formula?
I tend to plug in my numbers first and then solve for the unknown. Always write your formula, especially on free response, and then plug in the numbers. A lot of times there's a rubric point for, 1 point for identifying, this is a Newton's second law problem or a kinematic, proper kinematic formula. Then even if maybe you make an algebraic mistake, you might get partial credit for it. All right, acceleration due to gravity. It's not negative 9.8. It's negative 10 meters per second squared. We don't care about 32 feet per second squared. We use meters. So anytime you see 9.8, you need to use 10, negative 10, negative 10. Or as I like to say, 10 meters per second squared in the downward or negative direction, because sometimes you end up with, say, an Atwood machine problem where down may be your positive following the direction. So these two graphs, this is an object in free fall that's dropped. If you drop an object from rest, its initial velocity is 0, and then its velocity is getting more and more negative. And we know the slope of a velocity graph is the acceleration, and it has a negative acceleration due to gravity, so the slope of that graph will be negative 10. Your position graph, it's losing more and more position for each increment of time because it's